Earth cloud. Cool. Hello, everyone. Thank you for joining us in our November 2024 dialogue session. Today, we have the privilege of having Professor Konane Bay with us. I'll pull up some information. Um, Konane received her bachelor's at RPI in materials engineering. She later completed her MS and PhD in polymer science and engineering at UMass Amherst, and then completed President's Postdoctoral Research Fellow at Princeton University. And since 2022, Konane has been an assistant professor at CU Boulder. Notably, she has received the NSF Career Award, and that's a really big award for those of you who don't know. Every single faculty member, it's kind of the dream thing to get. So congratulations on that and all of your accomplishments, and we're looking forward to hear from you today.
Thanks, Kyle, for the invite to talk. Yeah, the careers as of today, so that's brand new news. So today I'll be telling you a little bit about what my lab works on. Hopefully, if you have questions or it's too deep in the weeds, because sometimes I get there, let me know. But really talking about, we think about polymers, which are kind of like plastics, and engineered living materials, which are using bacteria to make new material systems and fungus. But today I'll tell you a little bit about our fungus work. And so what I've been always kind of inspired by is I've always kind of been in this soft material space. So like polymers or plastics, it's the research I've been into. And so polymers are kind of all over this bike where the tires are made of rubber. There's rubber on the handles here. There's even, let me change this to a pointer. Maybe. Um, and even to the helmet. And so the example I like to use is for this helmet is that if you get in a crash and the helmet falls off, it ends up that you get these microcracks and you're actually supposed to throw it away. And so we think about the fact that many plastics that we have are single use. They come from petroleum-based resources and they're not renewable. And we can't actually get rid of all the plastics that we have in the world. They have their uses, even if we try our best. And so what do we need to design this new material? And so we try to imagine a world where we could have a helmet instead of just throwing it away. I could add some kind of light or feed it something and make a regenerable resource or regenerable polymer on your helmet that heals and you don't have to throw it in the trash. And so this is where engineered living materials has kind of come from. It's the term was coined in 2018, and the idea is using bacteria or fungus, so microorganisms that you can control their properties, and they actually make their own polymeric matrix just by self-regenerating. And so they just do it by eating food that's around them. And so my group thinks about this not in the biology context, but can we actually understand design principles using these microbes to make new systems that for different applications, from either helmets for protection to even sensing or biotechnology. And so, as Kyle said, I'm an assistant professor in chemical and biological engineering here at CU Boulder. And I run a research group with currently 4 PhD students in a mixture of material science and engineering, chemical engineering, and biological engineering. And I also have an undergraduate. And we also, similar to the Ko'olaus, we have the flat irons in Boulder. And so my lab is called the Huli Materials Lab, where we think about the fact of the kalo life cycle. We can plant it into the ground. We get our roots and our leaves to make poi and lau lau from and create this. And then we replant the huli into the ground and create this regenerative life cycle. And so there's kind of 2 sides of my research group. We think about the mechanics of thin materials. So these are things that are ultra thin. We go down to the nanometer scale. And then more on the fabrication, how do we make systems that are informed by what we know in this thin state? And so in my lab, we actually design instruments to measure mechanical properties, so how things break of difficult to handle materials. So you can think about the fact that cling wrap is really hard to handle, but think about something that's 1,000 times thinner than that, and how do we handle that? And so we think about how do these things break, including biofilms. So these are bacteria that make their own polymers and they surround themselves. And then polymer films, which are actually in a coating on your surface of your glasses to even in your phone. And so we look at how those change in terms of the environment that they're responding to. We also use 3D printing in my lab to make new materials and use bacteria, and we print them into specific locations. So today I'm going to tell you kind of two sides of my group. One is on that mechanics side of where we think about how do we measure ultra thin films. And then on one of the projects that we work on is the engineered living materials, but with instead of bacteria, we're using fungus. And so why thin films are kind of giving you a little bit of this, but they're used kind of everywhere from the coatings on optics or even on your glasses. So that's like the anti-scratch, anti-glare coating to even in your phones. While we're not here to the flexible phone case, the idea is if we can make thinner polymers, we could make these thinner films. We even thinking about chemicals, so actually milk, how we make 1% and 2% milk. They put a thin film in, they filter it, and they get out that milk fat, but they ends up getting breaking down due to the fact that they push a lot of things through it. And so could you design something that you don't have to throw those filter membranes away, which they also use to make water, clean water. And so what do I mean by ultra thin? This is kind of a nice size scale from everything from a paper clip's about 1 millimeter, cling wrap or saran wrap is about 0.2 millimeter, a bacteria is about 1 to 2 microns. A polymer chain, so like a length of it, is about 5 to 200 nanometers. And so what we think about for plastics is typically your polymer chain size is much, much smaller than the thickness, which is here labeled as HF, than your thickness of your film. What I think about as ultra thin is I'm approaching that polymer size. So we think about what happens if I take that cling wrap and I make it 1,000 times thinner, and how does those mechanical properties change? And one of the things that you can think about is cling wrap's already hard to handle. If I take cling wrap and I look at how much force it takes to break it, it takes about a kilogram, which is about a bunch of bananas to break it. And if I make it 1,000 times thinner, it takes only a paper clip to break it. So you can think about that. That's so much less force. I can't even put a paper clip amount of force. I would break it right away. And so we have an instrument in my lab called the uniaxial tensile tester for ultra thin films, or TUT-TUT for short, which I developed during my PhD work, where we can actually measure the mechanical properties of these things by stretching them and measuring what's called the stress strain response. So we can look at how things pull and then actually how they deform using this really simple instrument. And so typically how people measure these is they grip two sides of a system. So I've had like my glasses and they pull it apart. But how you can't grip something that thin. And so how do we grip these systems? And so we take an advantage of what's called van der Waals forces. And so the idea is if I have an adhesive or something that's really sticky, you can actually put the same system on itself and it will actually stick to itself when you're this thin. And so we actually use van der Waals forces. And so there's no clamps involved. It's just by pure stickiness between the two systems. And so we can look at what we actually get out of our instrument is called a stress strain response. So we measure initially a linear regime. Here it then yields, so it basically performs. It's like if you have a grocery bag and you're pulling it and it starts looking a little bit thinner and it actually doesn't bounce back. That's what's happening here. And then you start getting more things and it keeps stretching, but it really doesn't come back. So that's called plastic deformation. So this is a 200 nanometer thick film. I consider this thick. No one else does. When you go thinner, so now approaching the molecule size, you still see the same, where the molecule size here is 25 nanometers, you still see the same response. But when I go thinner below that molecule size, we now get this brittleness where we don't see that really long stretching in our system. And so this means that we have a critical thickness limit where we can't actually go thinner. We aren't going to be able to make these flexible electronics that are super, super thin that we have to account for that. There's a thickness limit for these systems. And so we really think about these polymers. All I showed you actually is polystyrene data, which is what we make plastic forks out of. And it's also what styrofoam is made out of. But we've done other work, including things that are more flexible electronics. And so these are electronic conducting. So trying to make batteries out of polymers, to coatings that are on your glasses, which is actually polycarbonate, which is the one that protects it from anti-glare, and to even doing nanocomposites. So these are thinking about making pure water for membranes. So the other side of my group, Kyle, if I'm going over, let me know, is on engineered living materials. And so this idea is, can we make a polymer out of a bacteria? So bacteria or even a fungus. Bacteria use and produce their own polymers, where people typically take bacteria and embed them in a polymeric matrix. And so we're interested in using this fact that they are living, that we can make them as sensors, we can do drug delivery, we can even make soft robots with them. But how do we control the mechanical properties? And so we're inspired by the deep sea sponge, which make their own glass in underwater conditions without having to heat up anything. They just use the minerals around them and they make these inorganic glass systems. And so we use the same enzymes that they make this glass on with a fungus. My collaborator actually engineers these so that we can actually make an organic inorganic composite, similarly to the mother of pearl, which is really, really strong. And so we're interested, can we design these living systems that we get kind of the same strength as a mother of pearl? And so my students do it in two forms, if my slides don't get one. Zoom is making it unhappy. My students do it in two forms. One is in fibers. So my student Olivia Pear prints fibers and then can basically mineralize them. And we see a change. And again, remember, this is our stress. When we mineralize them, which is the addition of this, what's this called TEOS, we see an increase in that strength. And we actually see they are more stretchy. Whereas if we have a different form, which my student Alyssa does, is these mats, we see a similar response. We don't see as much stretchiness, where this is going to about 14% strain, so it can really pull them far, but we do see an effect of this mineralization. And so we're starting to build on to that. And so it's just telling you a little bit about how we can play around with how things break by either looking at how thin they go, or even how we can just add an inorganic layer to an organic system and look at those mechanical properties. And so with that, I'll take any questions. Yeah. Scott.
Cool. Thank you for your talk. If anyone has questions, you can either unmute and talk, or you can write it in the chat. I do have one question. So, I do some work with soft robots. We mainly use silicone materials that are well known and like made and stuff. Um, so going off that, I had two questions. One, how many replicates do you usually do for your stress strain curves? And the second one is like, do you think there's any types of new living polymers that are good to replace silicone level type actuators that are like pneumatic or fluid based?
Yeah, that's a good question. So we usually run 5 to 7 replicates right now. We'll be running more. Actually, I was having a discussion with my student before, because biology is a little bit more um different in turn about for silicones right now. What people are doing for the soft robots is they're using like silicones, embedding the cells into those systems. So they actually use like polyacrylamide. So we're not there yet of making a bacteria make a silicone, but we might be eventually, I would say. So not quite there. It's a hope and dream, as the the phrase got coined in 2018. Nice.
And another question, I think there's like bacteria or funguses that like degrade plastics and stuff. Like, I'm not sure if this is in your realm, but could you talk about like the potential life cycle? Like, could you have like a fungus break down a plastic and make it into a new plastic based on like
Yeah.
some structure you set up? Yeah.
Yeah, you can actually totally they're currently still working on that. Like my collaborator is actually using these same funguses and he's putting enzymes on them that break down plastics and trying to get them back down to their components. And then I don't know if they're going to feed them back into the bacteria to make new ones, but that is something people are definitely thinking about. There's a whole area at the National Research Energies Labs, like down the road from us, that's called the bottle network, and they think about this life cycle analysis for doing like polymers to bacteria back to polymers, and they have like funding from like North Face and like Patagonia and like all these different like textile companies too.
Well, does anyone else go on? Yeah.
Uh, I'd be interested. Thanks for this great presentation and congrats on the NSF career. That's awesome.
Thank
Um, th- yeah, I'd be curious in hearing more about like Tut Tut and your journey. Was that, I heard correctly, that that was like part of your graduate work and like
Yeah.
you created this instrument, or yeah, I'd just
Yeah,
love to hear
no.
more about it.
Oh yeah, no, I'm happy to talk about Tut Tut. So yeah, so I was initially handed this project when I was a PhD student, and the initial version of it was actually a Altoid can that I was given, and it had like a piece of silicon wafer glued to the top of it. And the thing I was given was make this more accessible. That's basically what my PhD advisor told me. There are only 5 versions of it in the world actually to measure these things. There's one at University of Southern Mississippi, there's one in Korea, there's one in Japan, and there's one here, and there's one at UMass Amherst. That's essentially the extent of that. And that's what my career proposal is on that instrument. And so developing it was mostly trying to figure out how can we measure, it was set up, if you know what an atomic force microscope is, essentially it's like a cantilever based method, and we can measure from the cantilever how much deflection just by beam bending theory, and we can back out what the forces are on our thin film in that. And so that was building that. I initially was like just doing weights and then figuring out that we could actually do fundamental frequency to figure out the stiffness of our system. And then one of the questions I kept getting asked during my PhD, which I didn't talk about this, the other version of the instrument, was what was the impact? Because there was actually a liquid supported system when I initially got it, was how does water impact the mechanical properties of like anything I was measuring? Because a lot of polymers are water sensitive. And so I worked on developing during my PhD a freestanding method that we could measure down to about 30 nanometers in thickness. Tut we can go about 10 nanometers, but our limits are about 30 on specific systems. Sometimes it's only 100, depending on like how soft the polymer is we're looking at. So yeah, I did a lot of instrument development, but I also like looked at the fundamental polymer physics during my PhD.
Super cool. Thank you.
Yeah.
Um, I guess easy question is like, are there any ways that your lab currently or in the future is looking to kind of integrate with the community or do any outreach? And how does that work if you are? Yeah.
Kyle, you know this because we just talked about this. Um, yeah, so the career proposal actually wrote it to do outreach. So it starts off in Colorado, where we're looking at connecting indigenous art to like material science knowledge, and trying to build up a curriculum here, and then start doing summer camps in Oahu the last 2 years of the grant, so like 2029 and 2030, and come out and like work out a part of that. So just trying to bring more material science into the community is the plan.
Nice. Thank you. It's
Yeah.
always like, it's always cool to learn how people are bringing back these kind of crazy, unknown research topics
Yeah.
back home. So that's really awesome.
No, it's fun to come back. Yeah, because I would haven't like actually haven't been back since 2019 because my parents live in Washington state. So pre-COVID. But I was texting Kanoho saying I might be coming this spring. So we'll see.
Awesome. That's really cool and exciting. Cool. Well, are there any more questions? Oh, well, 3, 2, 1. Cool. Do you have any last closing remarks other than that? I think we're
You know,
good. Yeah.
it's always fun to talk, even if it's a lot about some of the stuff we do in our lab. So thanks for the
Yeah.
invite, Kyle.
Yeah. Thank you for coming. I know you're on a later time schedule, but thank you for your time.
No problem.
We'll give a virtual round of applause to you. Thank you.
Yep. Thanks everyone for coming. Mahalo nui.